everyone, and welcome. I'm Jane Francis Dewberry. I'm looking forward to moderating today's session on mitigating risk for community lifelines and hearing the three great presentations we have. First up is Roger Lindsey, who's the Stormwater and Floodplain Management Practice Lead at Metro Water in Nashville, Tennessee.
Joining us in this virtual format. I think that we've all become better at using Zoom for meetings, but this is my first attempt to create a recorded presentation, and I will admit that it was a bit of a challenge. It's been 10 years since the historic May 2010 flood in Nashville, Tennessee. In any flood event, there are hundreds, if not thousands, of stories that define the experiences of the lives of the survivors. From the Tennessean newspaper, I had captured scores of photos. But just to show you a couple of shots that give you a sense of the danger and the damage caused by this kind of an event. This is a shot taken from the foot of Lower Broadway, where all the honky-tonks are. Opry Mills Mall and the Opryland Hotel, and in between them up to the right there is the Grand Ole Opry, the scene of some of the finest performance in country music history. Another shot of the Opryland Hotel. This, at the time of the flood, was the largest hotel in the world outside of Las Vegas. But it was an extreme event. It was defined by roughly 13 to 16 inches of rain over a 36-hour period over the entire metropolitan Nashville area. Indeed, over most of the western half of the state of Tennessee. There were 44 counties in the declared disaster zone. By any measure, a 13 to 16 inch rain event over a day and a half would be an extreme event. But some 8 years later, I was introduced to the term atmospheric river. And that was, in fact, exactly what we had in Nashville, an atmospheric river. I was having some discussions with some of the research engineers, Dr. Carrie Talbot, with the Corps of Engineers Engineer Research and Development Center out of Vicksburg, Mississippi. He's been involved in a lot of research involving atmospheric rivers, but predominantly on the West Coast. But they had documented a number of similar events in the Gulf Coast and the southeastern United States. And indeed, the Nashville flood had been caused by such an extreme weather event. Another slide in a presentation he showed me right in the middle. The two slides vertically here show the Tennessee flood, May 2010, $2 billion worth of damage. And you can see that that storm is generated over the kind of equatorial Eastern Pacific Ocean, kind of forming up behind Central America there, and then passing across the Yucatan Peninsula and then blowing right up through the middle of Louisiana and Mississippi and on into Western Tennessee. And you can see the vapor transport perspective below, and you can see where that flow of that energy occurs. And then this was another cover slide for a presentation: physical processes associated with heavy flooding rainfall. And once again, the focus is on Nashville, Tennessee, and that weather system coming across the Yucatan, right across the Gulf of Mexico, and then in this case, it hit a stalled cold front, and that's where it dumped. It's like flushing a toilet. It's carrying this high volume of water vapor. One of the other slides referred to the fact that sometimes it's considered to carry a volume of water equivalent to 10 Mississippi rivers. In this case, it dropped 493 millimeters of rainfall in 2 days. But what I want to talk about today, I mean, there are a lot. I've done presentations on flood damage from 2010, but I really want to key on water, wastewater infrastructure, in particular our drinking water plants here in Nashville. So I'll start off by just showing you a few slides of some of the damage that occurred. This is the K.R. Harrington water treatment plant, the front entrance to the filter gallery. Then another inset photo down below shows the electrical system, the substation behind the filter gallery facilities. and the extent of the water. I mean, this plant is located in the floodplain. It's on the banks of the Cumberland River and right at the confluence of the Stones River, as you can see up above the plant on the upper right photo. There's a picture of our pump room. The water level in this pump room is 30 feet deep at this point. The high service pumps that feed treated water into the drinking water system are on a floor level a good 30 feet below this catwalk. And then below that is a picture of the whiteboard that defined a very deliberate, defined shutdown process that we went through that allowed us to turn this plant off essentially before the floodwaters began to impact it. And it prevented a lot of damage, obviously got things wet, but when you consider high voltage pumps and motors and things like that, they were all shut down. And so they simply, in a lot of cases, had to be disassembled and dried and then put back together. The recovery after that, an enormous amount of work, because at this point we were at half of our normal water treatment capacity. We were doing a lot of expedited procurement. We had an enormous number of flood-related purchase orders and spent a lot of money. We put this plant back online in 30 days. Just 1 month later, we'd repaired 4 2,500 horsepower pumps, a lot of electrical circuitry replaced, clear well structure assessed. Ultimately, we identified a need to elevate our vents and our clear wells, but that's a component that we've not started yet. Disinfection and water quality testing and drying out records. We had a lot of records stored in the basement of these buildings. But out of that comes a list of mitigation related items. And in this case, you can see we talk about relocating our generators and our switchgear, adding some additional generator capacity. We want to be able to run the plant at full capacity, a full 90 MGD on generator capacity. To raise the clear well vents, we established that's something that we haven't done quite yet. And then to seal a lot of the wall penetrations. There were a number of our deep pipe gallery rooms and so forth that sustained damage simply by water coming through electrical conduit. And to elevate the chemical feed system, it had previously been located in the basement to the filter gallery building, and we've now entirely moved that entire system. All of the chemical storage and chemical feed system is now on a flood protected elevation at the rear of that building. One of our wastewater treatment plants, the Dry Creek plant, is located up in the far north region part of Nashville, right on the Cumberland River in the confluence with Dry Creek. And you can see that it extensively flooded. It took a couple of years to get that plant into full operational capacity, including its solids handling capabilities. But it went back online in winter of 2012. But out of that comes a couple of mitigation items. We are presently, we have bid and are presently under construction with a project to install a flood wall around that plant and to provide for some storm drain closures so we can prevent similar damage in the future. This is the Omohundro water treatment plant. Omohundro will also be more prominently featured in this presentation, but this plant was challenged. You can see the water is right up at the back of our large pump station facility right here. We bent a little bit, but we didn't break. And this plant was able to continue to operate at a full 90 million gallon per day capacity, which was critical during that 30 days when K.R. Harrington was out of service. The biosolids building is located at our central wastewater treatment plant, which is downtown, just downstream of downtown, close to our central wastewater plant, which is the largest of our wastewater plants. Facility about 10 years old that was built closer to the river, and there was obviously a lot of water around and in the buildings and the facilities. So a lot of repairs had to be affected. Went back online in September of that year, and a good number areas had been repaired. There were also mitigation items on the list. It's our objective to elevate electrical substations, consider some wall options to provide some flood wall protection kind of features at the biosolids facility. And then the system repairs, lots of water mains, lots of service lines, fire hydrants knocked over, out of the ground. All of that is work done by our system services group, and there was a good bit of work done to repair leaks in the system, especially working from less than full capacity of water treatment. Having leaks was disastrous, so those had to be repaired quickly. So at Omohundro, we talk first at Omohundro, the major components of repair, the switchgear and power generation building. That was critically important because we had a lot of problems with the reliability of our power feed into this plant. It wasn't able to handle surges. There were a lot of issues with less than full power feed, especially given that this was our only active plant for that first 30 days. Also, site access was an issue and a problem. One of the earlier slides showed the main entryway into the plant was underwater sufficiently deep that we couldn't bring vehicles down that road or chemical deliveries, make chemical deliveries or any kinds of deliveries. So it was important that we provide another way to get into that plant. We look at this slide, an aerial view of the Omohundro water treatment plant. You can see in this case, we're in a dry scenario. You can see how wide the riverbank is behind the pump station. In a red oval, that's where Pumping Station Road is, and it's that access road that was underwater and unable to allow us to get in with chemical deliveries. The green oval is the site of the completed new alternate access road. This is a major point of ingress to the Omohundro water treatment plant now. Prior to the flood, it was on land that we didn't control, or it came through land that we didn't control. And so it's an important component of what we've been able to do. Another view of Omohundro and Omohundro South, again, from a little bit of a different, in this case, north is to the left. I've shown, this is still under construction, but I show in the large red, yellow oval where that new access road is. The entire property to the south of the water treatment plant is land that was acquired by Metro after the flood. It used to be an old auto auction site, but now it's the scene and location of a number of major department facilities for Metro Water. All of System Services is based out of Omo South. Our analytical lab is here on Omo South. But it gave us a high place to come off of a highway, state highway, and the interstate highway just off the site to bring in a new access road that comes down a hill and then drops right down into the filter plant area and allows us to bring in deliveries regardless of how high the river is. The green oval is the site of the new substation and switchgear and generator building, and that's a component of this work that is really something that we're really proud of. This is the building, switchgear building and generator building. The brick component is a switchgear. We also installed a totally new electric substation with step-down transformers here on this site. And you can tell that, that it's a high-powered substation. It actually has a capacity to bring in 69 kV, which is power not just to run the Omohundro water plant, but a number of other treatment facilities that are in and around that area. But we can also power that entire campus from the power that comes to this substation. TVA is under an agreement to deliver power to this substation. And beyond this point, we control and manage what happens from here. It's totally redundant. It's one half does what the other half does. This is another view of some of the step-down transformers. on that substation site. And then to show you the switchgear. Switchgear really controls how we deliver power from that substation. And this is, again, is another totally redundant system. The front half of these switchgear banks, all the way down to this break in the middle, is redundant to the back half. It gives us full capacity to use one side or the other side, depending on conditions or problems or issues. The other thing that's significant about this, at some cost, all of these switchgear cabinets are gas charged. They are charged with a gas that eliminates the ability for arcing. And so we're able to get by with half of the size of the cabinet that we would otherwise have to use. That makes the building half the size that we would have used with the old traditional switchgear that was not gas charged. So it's a real novel system. Just to the left of this picture, on this wall to the left, is a control panel, control room, and we're able to do a lot of switching and work with the controls in that room. And then behind that switchgear building is a generator building itself. And this is the building that houses the 4 Caterpillar generators. This is a close-up of one. This one large Caterpillar generator has a 2.5 megawatt capacity, and each of the 4 have that same capacity. So we have the capacity to generate 10 megawatts from these 4 Caterpillar generators. And I can assure you that when they're all 4 running, you can't have a conversation in this room. One of the things that's really important and interesting in this whole concept of power feed is that we are under an agreement, a contract with TVA. We're one of their largest customers, and we have, with the request from TVA, with 1 minute's notice, with 60 seconds notice, we can go totally off of the public power grid and feed and run that plant just off of the power generated by these 4 generators. It's a remarkable system. We can run all the things that we need to run, feed our entire campus for weeks, even months, as long as we can continue to bring in tractor trailer loads of diesel fuel. So these are 3 25,000 gallon tanks, and they power those emergency generators. Remarkable system. It goes toward the effort that we have to team and partner with TVA. If we get in the middle of an emergency, or if we're in the middle of a hot August and they need power, with 1 minute's notice, we can drop totally off of their system and allow them to distribute that power elsewhere. And as a result, on 365 days a year, we get a preferred power rate for the power that we do use. So it's a win-win for both of us. A year ago, we had a tour with former FEMA administrator Craig Fugate. Also present at that tour was our Tennessee Emergency Management Director, Patrick Sheehan. Commissioner Administrator Fugate came to town with the Pew Charitable Trusts and for a series of meetings. And while they were in town, we were able to bring them out and show them both of these water treatment plants and the work we've done with the mitigation. And again, all this mitigation work was driven by the fact that we had experienced this flood. And so it was our intent to do the things that we needed to do to improve the reliability and the dependability of all of our water treatment facilities. So Omohundro, what does this do for us? We spent $43 million on this project, started construction in 2017 and finished it up last spring. It gives us unimpeded access to the water plant through this new access road, reliable power for all Metro Water facilities at or near the Omohundro facilities. And again, the ability to provide full treatment capacity on generator power and the ability to drop off the TVA grid. Those are really significant things, and it was really an incredible project. KR Harrington is the other of the 2 major drinking water treatment plants that we operate here at Metro Water. And the major components of our mitigation work there. Again, this is a plant that had flooded. It was out of operation for 30 days. We had a lot of work to do in the filter building. Built an entirely new electrical building and switchgear system at a much higher elevation. We elevated the raw water pumping station by about 4 feet. There was a replacement of all chemical storage and feed systems. We built an on-site bleach generation system, which is part of a long-range plan that we've had in the works for a good number of years to eliminate the handling of hazardous materials. By being able to generate bleach on site, we eliminate the need to handle gaseous chlorine and those kinds of things. Critical facilities, everything was elevated to the 500-year plus 2 feet level. So here's an aerial view of KR Harrington. Much of this plant, the earliest phases of this plant were built back in the 1960s and early 1970s. The large building that you see in this area is our new switchgear and generation building. The small building in front of it is the old switchgear and generation building. And I'll show you a good number of more of additional pictures of that. This is the raw water pumping station over here. That's where we elevated our pump shafts, extended our shafts, and elevated the mountings for motors and the electrical control system. So this facility is protected to a much higher elevation than previously. And then on the back side over here, we'll show you pictures a little bit longer that the on-site bleach generating system. So here's a picture of it during the flood. Totally flooded. It's on the banks of the Cumberland River and the confluence of the Stones River, which is one of our major drainage basins just downstream of the Corps of Engineers dam, power generating facility. So you can see the extent to which this facility was surrounded by water. This was the old generator and switchgear building, water in it. Water came into the sublevels of this building and traveled all the way back to the filter building through the electrical conduit. And that's one of the pieces that we fixed as we started our mitigation work. This is a good shot of the new switchgear and emergency generator building. You can see the old building in front at a lower elevation, a much higher elevation for the building behind. And here I've placed a couple of, the red line shows the rough floor elevation of the old generator building, and the green line shows the rough floor elevation of the new generator and switchgear building. Again, a nice aerial oblique view of that building. All of the switchgear for this treatment facility are located on the second floor of this new building, some 10 to 15 feet higher than previous elevations when they were damaged during the flood in 2010. And of course, the 5 generators, you can see the air intakes along this side. The chemical feed systems used to be in the basement of the filtration building. Now they're all located at a high elevation on the back end of the filter gallery, the filter building. They're all totally brand new feed systems. This is alum feed, the carbon feed system, the lime feed system. All of the chemical storage is on the back end of that building. Again, at 500 plus 2 feet elevations with additional flood wall surrounding it to provide for dry flood proofing. And then again, the on-site bleach system just to the north of the clarifiers. Tanks for salt storage and chemical storage. Again, this has proven to be a really beneficial system to use on site, allows us to accomplish our disinfection of drinking water. So KR Harrington, what does this do for us? Provides the ability to operate, again, at full treatment capacity on generator power. There's not quite the system here as there is at Omohundro. We have totally updated switchgear and power controls. even a lot of the control boxes on equipment in the filter gallery, the pipe galleries, the deep, low piping facilities within this are utilizing sealed control boxes to prevent the level of damage that occurred during the flood. On-site bleach generation and again, flood protection for raw water pumping. And what this does is it ensures an expedited return to full service following a similar extreme event. We were out 30 days during the 2010 flood. Following the 2010 flood, we would expect to be back in operation in half that time, given the nature of the events that we've put in place here. So with that, I would be glad, and I will go live and answer any questions you may have.
Great, thanks, Roger, for that great presentation. We had a couple of questions in the chat that you and I have talked about, so we'll start with the first one. For the water treatment plant, how'd you calculate generator needs? Was it on the full plant or just a bare minimum, and how long?
No, and the absolute intent was to be able to run at full capacity, and both of our water plants are capable of 90 million gallons each. So both of these new generating systems are sized to run at full capacity.
And for how many days?
Harrington, is a little bit different because it's in the deep floodplain along that river. The Omohundra plant is up on the generating facility is up on the hill, and it can run for months, literally, because that's the one we really have the deal with TVA, where we can drop off their grid and we can just keep hauling in tractor trailer loads of diesel fuel, and we'll run it for months if we need to.
So these are not the generators I can buy over at Lowe's then?
No, not.
So how did the mitigation projects impact your CIP?
Well, the initial work on these plants, getting them back in operation in the case of Harrington, we used FEMA public assistance funds to the extent that it was available after the flood. There were so many needs, so many demands for the dollars that were available. So it's been 10 years. We literally just celebrated the 10th year anniversary of our May 2010 flood. So a lot of this work has come to fruition in the last 2 to 5 years, and a lot of it's been funded with local dollars. We've been able to get some a good increase in recent years of our water and sewer rates that has kind of opened a new capital budget for us that we can continue to use to continue to do mitigation at these facilities, as well as some upgrading at some of our wastewater facilities.
So talk maybe a little bit more about what your other plans in Nashville are for doing further mitigation of water and wastewater.
We still have, obviously the work at the Dry Creek wastewater plant. That's a flood wall type project that has now been bid. And so that project will get underway soon. And then the biosolids facility as well needs some consideration for flood protection, and probably a flood wall type project for that as well. There's a lot that's going on in Nashville. We continue after 10 years to buy and demolish homes. Our buyout program, we've bought and demolished about 400 homes. We call those houses that will never flood again. We've also done a lot with respect to flood forecasting. We developed a flood forecasting tool, Nashville Safe, which I actually presented on a little bit 2 years ago at the national conference. Just conformance with NFIP requirements. We're sticklers about elevating houses. We have a 4-foot freeboard requirement in Nashville. So
that's incredible.
New homes or substantially damaged homes have to be built 4 feet above base flood elevation. It's a regulation, an ordinance that's been in place since 1979. And we in research done by Vanderbilt University, we believe that we saved probably as much as a couple $2 billion in damages avoided because every house built for the last 30 years has been built 4 feet above freeboard base flood elevation. So that's a big part of what we do to try to avoid damages.
Absolutely. Great. Well, thank you so much for the presentation and for the questions and answers.
Certainly. Thanks so much.
Yeah, our next presentation is by Joseph Albani, who's a project engineer, and Jake Oldenberger, who's a project manager, both from Tetra Tech. And they'll be speaking on work that they're doing with the Port Authority of New York and New Jersey.
Hello and welcome to the JFK International Airport Stormwater Outfalls and Port Newark Building 111 presentation on mitigation.
So how long is
my name is Joe Albani and I'm joined by Jake Oldenberger.
Thanks, Joe. Just a little background. Joe and I both work in the New York City office and have been working on these type of resiliency and mitigation projects for the last few years. And we're glad to be here with you guys virtually as it is, presenting these projects and discussing a little bit more about how mitigation risks are implemented for these major community projects. So with that, I'll talk about the objectives of this presentation. We're going to talk about a little bit about the FEMA funding programs and how they are applicable for the design of mitigation. We'll also discuss how mitigation is implemented and how it ties hand in hand with that funding. And lastly, also talking about evaluation of the client design guidelines. Just because these projects or the projects we'll talk about were FEMA funded doesn't necessarily mean that other design guidelines and level of protection standards wouldn't be implemented, such as state or local requirements. So that's a major point here, and Joe will be talking about that a little bit later in the presentation. So for these projects specifically, we're going to talk about two the FEMA funding programs specifically, which are dictated by the Stafford Act, sections 404 and 406 of that act. They're referred to those names. Section 404, also known as the Hazard Mitigation Grant Program, HMGP, provides the funding for declared disasters to undamaged parts of facilities. And that's the key difference for the 404 program from the 406. And it's to reduce the damages from future disasters. But it's tied to like the undamaged areas or facilities that would provide mitigation and protect a larger area that wasn't necessarily cannot do mitigation specifically for every piece of structure or item. The Section 406 program is part of the public assistance program. It's similar, except it's specifically for mitigation of direct damages to a facility, and with the goal of preventing similar and damages from future storms. So if a transformer got damaged, you're looking at mitigating that transformer. That would be part of a 406 program. An example of a 404 program would be, which we'll talk about, doing some implementation that protects a larger area, or a dam that would have some increase in mitigation, protection that would protect downstream structures. So a little background just to center ourselves. So we're talking about JFK International Airport and Port Newark, Building 111, which are circled here in red on this map. Just to give you guys all a background of the Port Authority themselves, it's a little different than how people may be understanding of a Port Authority as in charge and operating the main ports. The Port Authority here in New York City in the New Jersey area actually operates not only the ports, but the airports, JFK, LaGuardia, Newark, directly here in the city, as well as Teterboro, a smaller regional airport. There's also one further upstate north of the city, but they're also involved with all the a lot of transportation links, the George Washington Bridge, Lincoln Tunnel, Holland Tunnel, bus terminal, and also World Trade Center, in addition to some freight and passenger rail transit that comes in and out of New York and New Jersey. So it's a wide different types of services and operations that they have. And talking about that and why Superstorm Sandy, which was really the direct driver for these projects, as you can see by the numbers on this, it was a large major scale disaster for the New York area. Huge economic losses for both the city and specifically the Port Authority. As we just talked about, it was more than just their ports, their airports, their container yards, but also the tunnels that got flooded, buildings, basements of their facilities that got impacted and were out of service for long periods of time. That was a huge economic driver. And so why this is a very crucial component, because not only are we moving freight, as you would hear from ports, but we're also moving people throughout the city. So the types of mitigation projects we'll talk about for these two areas include both permanent deployable flood barriers. We looked at raising equipment and backflow prevention. Each one is a unique kind of different tools you would have in a tool belt that you would look at for these projects. So we're just going to talk about a few of these just to give you guys examples of these. So to orient ourselves here, this is JFK International Airport. We have pulled up here on the right side is the effective FEMA map, just to give you some perspective. Superstorm Sandy within this area had a high water elevation of roughly 11.2. Based on the effective maps at the time, the base flood elevation was roughly elevation 8 in a different datum, which corresponds to about elevation 7. So about 4 feet higher than the base flood elevation at the time of the effective map. Some preliminary maps have come out. That's what you'll see in the lower left corner here. The base flood elevation, it varies throughout the airport. It's obviously a large facility, but it roughly is around elevation 10 for the most part. If you can see closely, that area shaded in blue is paralleling the edge of one of those runways. And that'll be important when we'll talk about. But I think the hurricane from Superstorm Sandy, the surge reached up to even higher than that. So it inundated and got up over on to some of the runways at JFK. So for this part we're talking about is the 406 component of the airport. Both 406 and 404 funding was implemented here. But for this area, the 406 program was directly tied to damages of the electrical lighting system at the airport. Along all the runways and taxiways, there's the lights that illuminate them for the pilots when they're landing and moving around and taxiing. There's thousands of those lights throughout an airport, probably tens of thousands. And all those are flush with grade, obviously. Because of that, they have sumps that are tied directly to the drainage system, which then ultimately discharges out into the bay. As you can see by this figure, when the storm surge hit, it kind of inundated up through the pipes and up through the outfalls, up into the cans and flooded the conduits. The major issue with this is salt water, which corrodes all the electrical lighting system. But not only that, but because as I mentioned, it got actually up over some of the low points around the perimeter of the airport, which also caused inundation further inland that got into the system. As you can see, airfield operations ceased for over 35 hours at the airport. That's obviously a huge loss from passenger transit, but also cargo in and out of the airport. So for this project, there's over 20 outfalls at the airport, specifically tied. This part, we looked at 17 outfalls that were directly correlated to the area where these light cans are. Two alternatives we looked at was a backflow prevention at the outfalls themselves. This was obviously a substantial project that would be evaluated and contemplated because some of these outfalls are enormous. So we're talking in some cases box culverts. The other alternative we looked at, because of how large these outfalls are and how custom these outfalls would require custom types of backflow prevention, would be smaller implementations at all the light cans, manholes, and handholds. As you can imagine, with over thousands of lights, there's probably another over thousands of other junctions and everything that would be sealed. So obviously each has their pros and cons. Ultimately, alternative A was chosen based on the cost, the level of protection, and the disruption to operations. And it also provides the ability, as they go look at protection future as climate changes, are evaluated for raising and providing higher levels of protection if they look to increase the perimeter. So types of outfalls protection we looked at was flap gates, duct bills, side gates, inline protection, was different items that we looked at as part of the preliminary study to understand what options we had. So just an example here as the image is alternative A, which was flow prevention at the outfall. As you could see, by doing that, it would seal the pipe there. No water would come up into the system, and it would also provide, and then this option was some type of road raising or perimeter protection that prevented a similar event from going over tops of some low points and preventing it from getting into manholes further inland and then flooding back. And this is an image of alternative B, where that backflow prevention was actually put at the light cans themselves. So you would still have the same event. Water would still get off for some low points and come up through the system, but it would be stopped at the cans. As you can see, there's a lot of different pros and cons, and obviously cost was a major driver as well. Another part of the work that was done at JFK Airport was the another set of group of outfalls. Specifically, this was centered around the fuel farm area of the airport where all the fuel is stored and then pumped to the planes. For this area, actually the 404 program was utilized. This was to prevent the fuel farm from flooding. So this was tied to backflow prevention there at the edge. The shoreline was actually higher in this area, so they provided some backflow prevention at the outfalls to prevent any fuel farm from future damages from happening. There was none that nothing significant happened in the fuel farm area, but so it was more designed for future events that could come into play. And this was actually one of the first programs that got implemented at the airport. So as part of the preliminary and final designs as we looked through, we looked at the 5 outfalls or outfalls 2 through 6 at the airport. Different types and sizes. Mostly the preferred option for this was a flap gate. This was based on owners and the operators, the maintainers out there at the airport preference, because they could get out there and exercise these gates and make sure and clear any hot debris that got in there. To assist with that, we looked at providing double chambers with an upstream chamber that would provide an area to capture sediment and skimmers with in there so that no floatables would be caught to minimize and reduce the amount of maintenance over time. With that, I'll turn over this presentation to Joe, who can talk a little bit about the construction of these first 5 outfalls that went in at JFK and also Building 111 project.
Thanks, Jake. So with the 5 outfalls project, we took these from planning through design and then through construction. And they had their own issues, just like every construction project. But there were certainly some specific to JFK that we had to deal with. Obviously, getting security access, not only for the contractor, but also for inspectors, geotechnical engineers is a bit of a hassle over at JFK to execute this project. We were also given a pretty narrow corridor because these outfalls were located on the exterior fence, security fencing for the airfield itself, but we were up against the ocean itself, so we had a very narrow corridor in which to do our work. And obviously, whenever you're doing outfall work, you have to deal with tidal construction issues. Dewatering was a constant issue, particularly for Outfall 6, where we had to do actual excavation. Outfalls 3 through 5 were actually pretty typical flapgate installations. They were between 4 and 5 feet square, and they were externally mounted on existing outfalls that had pretty good concrete. We fit them in against wing walls. We had security fencing on the exterior, and we had floatables catchment upstream of the outfalls to keep them operating appropriately. Outfall 2 was a little bit different. That was a particularly large culvert. The existing outfall wasn't in great shape, and it also had actually deteriorated between the design phase and construction. So when the contractor got to the field, he found that the outfall was not in as good a condition as we had originally thought. So we had to do some initial testing, and that design actually had an interior sleeve to help support the large outfall structure. We also had to install trash grates well upstream because this culvert didn't have easy place to put a manhole to put in trash catchment. So we actually had several trash grates installed in tributary manholes upstream, which had their own issues because we didn't have exactly the information we needed to properly design these trash grates. So we had to do a lot of redesign in the field. And then Outfall 6 was actually probably the most difficult installation. We had originally planned on a dual chamber system, one with the flap gate and the other with the skimmer, because the existing outfalls really falling apart, and there was no way it was going to be able to support the gate that was required. When we actually got to design, or when we got in the field, the contractor hit numerous obstructions because this entire airfield was filled with material, and there was very large boulders, and it was really slowing down progress, especially working between the tides and between the existing security fence and the water itself. So we had to do some design changes in the field that ultimately delayed the construction timeline. And I think it's important to spell out these potential pitfalls, especially to the client and the contractor as best you can before you get in the field. So if you want to go to the next slide there. So just a summary of the challenges that we actually encountered for the stormwater outfalls, both the planning and the design and implementation of these projects. It's important to evaluate all your mitigation options early, especially for that 17 outfalls project. You have to look at road raising or gates at roadways, flood walls, just because you can't just install a backflow preventer at every 1,000 light cans. It doesn't give you the same level of protection either, because these light cans are at different elevations and you're still prone to overland flow. Another item to look out for is just special circumstances for the work that you're doing. We installed backflow prevention at a fuel farm, so it's definitely possible that you can get leakages of diesel fuel or jet fuel. So we didn't want to use materials that would be severely impacted, such as a rubber product. Should also, it's always good to emphasize the need for on-site investigations, whether that's extra borings or test pits in fill areas, or we realized in construction that we needed a better inventory of the existing manholes for trash grate installation, just because we couldn't get them to fit. To go along with that, just being able to identify potential changes during construction and seeing how those lead to, further changes in design. Say hitting large obstructions, you don't want to, completely change your plan of construction just because you hit a few obstacles. It's also, especially in this project, we realized how important it is to give, your construction crew enough laydown area. If we could go back, we would have strongly proposed to relocate or temporarily remove the fence that really impacted our excavation area. It's also, whenever there's marine work, you have to emphasize how difficult it is to work within the tide and execute your construction, both with the contractor and with the owner. And then finally, it's important to take as much information from the operators as you can really get out of them. Because at the end of the day, you're leaving them with this product. So you need to get their input and get their best practices implemented. And now I will talk about the Port Newark Building 111. This building is the high service pump station for Port Newark, which is a marine terminal for container ships. And what it does is supply domestic water as well as high pressure fire protection services to the entire port. This is a 406 project. It was heavily damaged during Superstorm Sandy. The existing building elevation is about 8.5 NAV D88, which resulted in approximately 3 feet of seawater flooding the facility and damaging a lot of critical equipment during the storm, and put the facility down for a number of hours. Right then, temporary repairs were made to get it back online. In the ensuing months, interim mitigation measures were implemented just to make sure it stayed operational. If something else happened. In the meantime, luckily the large external water storage tanks and the pipe servicing the building weren't damaged, and FEMA, pretty quickly decided to raise the base flood elevation in this area. So the base flood elevation was 9.0 NAVD88, and they raised it to 12 NAVD88 after Superstorm Sandy. This is still a preliminary map, but it's what we need to design for, given that this project is a long-term project. And in addition, we need to follow the Port Authority's new resiliency guidelines as well as the local codes. So the Port Authority over the years has developed a resiliency guideline, and that went from a memo to a full-blown resiliency guide. It's really focused on coastal sea level rise and making sure if you're putting in a new facility, that it's designed both for local code, FEMA, sea level rise over time, and the necessary freeboard. So they developed this actual pretty simple graphic. You just go through the steps for this particular site. Item 1 is, are you in a FEMA floodplain? And obviously we are here. So you answer yes and move on to step 2, which is your asset service life. If your facility is going to be operational for less than 30 years, then you only need to add 16 inches of sea level rise adjustment. And these are based on the 2015 median sea level rise expectations. Obviously, they will update this over time as the understanding of sea level rise is better understood. And the longer you expect your facility to be in service, the higher you need to adjust your sea level rise. And then the final step is to define your asset as critical or non-critical. Obviously, this is a high service water service building for the port itself, so it's very critical. So we had to add 24 inches of freeboard to the already implemented sea level rise adjustment, and that leaves us with a facility design flood elevation of 15.33 NAVD88. So just comparing that to the existing condition, that is approximately 7 feet higher. So we went through 3 options with the Port Authority to determine how to proceed with this project. First was to elevate critical electrical and mechanical equipment. Second was to dry flood proof the building. The third was a hybrid of elevate and dry flood proof. We ended up going with the elevate option just because the client really did not want to implement dry flood proofing measures, which really require a human intervention and have a higher susceptibility to failure as opposed to simply elevating a product. So that's elevating your pumps, controls, relocating equipment outside because we had limited ceiling heights, switching your pumps from a vertical orientation to a horizontal rotation, going with elevated transformers, flood barriers. We looked at backflow prevention, obviously, for the sanitary sewer line. And ultimately what we landed on was elevating everything that was critical. We elevated, or we're planning to elevate all the critical electrical control panels in a building addition, actually exterior to the building with higher ceiling. We're going to elevate an external generator and the utilities transformer for them. We're going to replace the pumps to make them a horizontal orientation, as well as elevating them on a platform, and the diesel engines to run those fire pumps and put it in a sanitary sewer backflow, and actually allowing the building to flood as the structural improvements required to retain 7 feet of floodwaters is not cost effective. So some of the challenges here is really just understanding the client's goal early on, just knowing what's critical for them, and verifying the existing conditions is very important. Basically, we had limited ceiling room, and we needed to know exactly where every pipe was and how high we could go before we reached the threshold of needing to move components exterior to the building. We also had to coordinate with utility providers because we have a transformer that's supplied by the utility that was damaged. They want to give us a new one, but we want to elevate it, so there's some coordination there. There's also, you need to identify all points of failure in floodproofing. Dry floodproofing can fail from, structural issues to, it not being installed properly or not being tested properly. So it's a real risk if it's not done well. And then the last item is just to carefully consider construction sequencing, especially for a facility that can't shut down. You need fire prevention at all times. That's even if you're upgrading the facility to be ready for the next superstorm. So in summary, this is the mitigation that we implemented and are implementing at the JFK International Airport in Building 111 due to Superstorm Sandy. Mitigation funding programs, Section 404 and 406 for facilities that were damaged by the storm or could potentially be damaged by a future storm. We walked through all the mitigation that we are implementing at these sites or have already been constructed. And, we went over how important it is to go through, your clients' priorities and guidelines to give them the best product that they need. So with that, we'd like to thank you for your time. And Jade.
Yep. Thank you very much.
All right, thank you.
Great. Thanks, Joe and Jake, for that presentation. I was looking at the Q&A as you guys were speaking. There were a couple of them. The first one, did Alternative A require mitigation to the adjacent properties since you were raising berms and roads there around the vicinity of JFK?
Great question. So JFK is an enormous property, as you know, with multiple. I think there's up to 4 runways there. So any of the improvements, we looked at this at a high level. That honestly, this is still being something being considered by the Port Authority and how high the berm will get. So depending on that, will be the extent of the impacts. But for the most part, it would mostly stay with it. All of it, I believe, will stay within the property of control of Port Authority.
Just kind of diverting it away from the critical areas.
Correct. Yep.
Yeah. Okay, cool. And then what method did you follow to understand how to design for sea level rise?
So we actually have to follow the Port Authority's resiliency guidelines, and their guidelines were developed well in the past, but most recently based on 2015 guidelines for sea level rise. So, there's a lot of different ways you can point to how to select your sea level rise to take account for. So really, Port Authority just sets it for the client or for consultants to work with. So, you don't have much leeway there.
It makes it a little bit easy.
Yeah, exactly.
Okay, so we have another one that just came in. Are you creating elevated access to Building 111 to access operations during flooded conditions?
So Building 111 is actually going to be allowed to largely flood during the storm event.
Okay.
As we go through the design, we're going to consider how we actually have employees actively in the building to operate the facility. That's why we're still in the preliminary design stage. That's one of the key considerations moving forward with the Port Authority. But just going through the rest of the process with design is how we ended up with elevating, individual components as required.
That'll be a complex kind of marriage of mitigation and response then.
Yes, exactly.
Okay, cool. And then I had a question while listening to you is you talked about coordinating the 404 and 406 programs. Were there any challenges in that?
One of the challenges was when it came to defining the benefits as part of the BCA component is making sure there wasn't any duplication of benefits. So if there was a claim that this level of this project would protect about shutting down the airport, we couldn't claim it on the other project as well. So there had to be a balance between that. And that was really in the BCA phase to feather that out.
Yeah, that's always important to get that BCA nailed down.
Yeah.
Great. Anything else you guys want to cover that you maybe didn't get a chance to squeeze into the presentation?
I would just say that we're still working on these projects. I heard the previous presentation there. They just wrapped up about 10 years. We're about 8 years, coming up on 8 years after Hurricane Sandy, and we're still working on projects. There's still a lot in the pipeline to come through, and it's just very interesting, and a lot to come to see in New York City.
Awesome. Great. Well, thanks so much, guys.
Thank you.
So our final presentation is from Kiran Konduru, a senior professional engineer with the city of Fort Worth, and Holly Amata, an engineer and project manager at Friesen Nichols. They're going to speak about Fort Worth's Hazardous Roadway Overtopping program.
Hi, my name is Kiran Konduru. I'm a senior professional engineer with the City of Fort Worth Stormwater Management Group. Along with me, Holly Amda from Friesen Nichols will also be presenting. I want to start off by saying that we have an enormous challenge. There are a lot of high-risk hazards spread out all over the city of Fort Worth. So the problem is, how do we tackle such a challenge with the limited resources we have and the time urgency set by the council to be able to address at least some of these challenges and get significant on-the-ground improvements? So what you're about to see is what we have done and how we are solving this huge challenge by providing you with an insight into Fort Worth's Hazardous Road Overtopping Mitigation Program. Next slide. So what is a hazardous road overtopping? It is typically a low water crossing that have undersized culverts or bridges which only have capacity to convey flows under the street for low flow conditions. And under high flow conditions, water run over the roadway and prohibits vehicular traffic. And these water crossings can be very dangerous when flooded. So it is a hazardous road overtopping. The pictures that you see on this slide show a spectrum of such crossings we have in the city of Fort Worth. Vertical down, the first column shows small culverts which are undersized. Second column shows culverts much bigger and are also undersized and have no protection like guardrails or safety features. Often these were inherited as the city has annexed regions. The third column shows bridges which are large undersized culverts, and the public may not expect the risk at these crossings and are more than typical low water crossings. Next slide. The pictures in the slide are a few examples of how the crossings look in a wet weather condition. So we have three basic approaches we are using to reduce hazardous road overtopping. One is to reconfigure the crossing in some way to reduce the level of overtopping. This could be done by raising the roadway or making the opening under the roadway larger. Another way is to add safety enhancements to the roadway crossing without reconfiguring the roadway. This approach includes measures such as guardrails, signage, or improved lighting. And the third one is closing a section of the roadway in the immediate vicinity of the crossing wherever it is feasible. One thing I want to mention here is it is not practical to completely eliminate the flood risk for the roadways. However, the hazardous road overtopping mitigation program will significantly reduce hazards with reconstruction or road closure. The program will also manage residual risk with safety improvements on a hazard priority basis. Next slide. Fort Worth experienced severe flooding in 2004, where there were several incidents reported, which led to the creation of a committee to provide recommendations to the council. Based on the recommendations from the committee, the council took action and a separate stormwater utility fee was established in 2006 to fund stormwater projects. Since the stormwater utility was created in 2006, we have reduced road overtopping hazards at several locations. Approximately 20 sites were improved with CIP and partnership, and approximately 50 high water warning system flashes were installed. But the improvements needed are expensive. Some funding must be allocated to fund other needs, and the resources currently available are enough to improve only few locations. So establishing a program allows us to take a proactive rather than a reactive approach to mitigate and to optimize where the dollars are spent. In 2018, our stormwater management program master plan was adopted, and there was flooding in 2018 and 19, which led to creation of this program. Next slide. The city of Fort Worth completed its stormwater Program Master Plan in 2018, which identified the need for a greater emphasis on projects with critical life safety consequences. The city determined that hazardous road overtopping locations carry some of the greatest life safety consequences. As part of our mission to protect people and property from harmful stormwater runoff, the Hazardous Road Overtopping Mitigation Program is one of the focused effort to achieve this mission. The program addresses two elements. One is to mitigate hazard through capital projects, and the other is to warn community of hazards to increase safety measures to communicate flood risk. Next slide. So since 2006, the Stormwater Management Division has worked on reducing road overtopping hazards at several locations. The fee has not increased since January 2012, but the flooding that happened in 2018 and 2019, we have experienced several flooding incidents and had media attention, and it had such an impact on the city that we were able to get a fee increase and put additional funding into this program for solving the problem. Next slide. So the funding for this program comes from the stormwater utility fee. The stormwater utility is a monthly user fee that pays for maintenance, improvements to the storm drainage system, and other stormwater program activities. There was a recent utility fee increase of 6.5%, which provides an annual revenue increase of approximately $2.6 million. And along with our plans to sell $70 million in revenue bonds in FY20, we plan to use at least 35% of this bond sale towards this program, with a focus on expediting the delivery of capital projects and addressing critical life safety needs. Next slide. So this slide shows the program phases. This is an asset management style approach that have data-driven decisions for mitigation. And to optimize funding, the program includes all phases of hazard reduction, from identification of hazard locations, priority-based ranking, developing solution concepts, engineering design, and construction. Next slide. So as I was saying earlier about the enormous challenge we face, this map shows a spatial spread of the enormous challenge we have. It shows more than 300 hazardous road overtopping sites spread all over the city. Next slide. So what risk have we experienced in the past? There were 12 sites with fatalities, and since 2009, we have been tracking the incidents that were reported in GIS. And since 2009, there were a total of 63 rescues reported and 251 instances where the sites were barricaded, and a total of 721 flooding reports. I want to mention that there were a lot of incidents prior to 2009 that were not captured in the GIS. Next slide. So we define anticipated hazard in three terms. One is how deep the water is over the roadway. The second is how frequent the roadway is submerged. And the third is how hazardous the downstream conditions look like. And what we tried is to put a scale to help us understand the worst of the worst locations and focus on that. Highlighted in red on these pies show the greater risk. Next slide. So this slide is a combination of the previous two slides to create a well-defined hazard score as best we can characterize. We took the engineering and combined with it with historic objective. Also, we continuously update project priorities as new information becomes available. There might be several instances or there might be several sites that might have the same hazard score. And in such cases, we use some of the tiebreakers that include technical and community values, such as traffic count, velocity of the flow that is overtopping, and whether the site is in a super majority minority area that have been historically underserved, and also any other partnership opportunities. With that, I will pass on to Holly.
Thanks, Kiran. So like Kiran was saying, this hazardous roadway overtopping program was broken into several phases. And at each phase, we tried to take an asset management style approach to reevaluate where to best spend the city's resources. So moving from the 300 sites that we were looking at during the identify hazards phase, moving into the prioritized locations phase, the 50 most hazardous sites were selected for additional analysis. So for these sites, we did a preliminary hydrology and hydraulics analysis, and we used best available data for each hydrology and hydraulics to establish a planning level, 100-year level of service, size, and associated costs. And this was really focused on understanding the scale of costs for these major improvement projects. So how those projects broke down. So we had kind of 4 categories that these planning level costs went into. So for Fort Worth's hazardous roadway overtopping program, $3 million on average is what we expect to be spending on a major improvement project. And so any projects from this planning phase that had a cost estimate $4 million or less went into this first category of ideal for this program. Then the next range, which is the yellow, was $4 to $6 million. These are sites where the major improvement with additional design refinements could fit into this program. And so there are sites to consider moving forward. And we then have sites shown here in orange, which are program feasibility and unlikely to fit the program. And so for large bridges require change in the roadway elevation. And so while these sites, may be a good project, it's just outside what's feasible in this program. And this information is great for the city to have still. It's something that can be leveraged in the future if a partnership opportunity potentially arises. They already have a pretty good understanding of what a major improvement should look like at these locations. As part of this prioritized locations phase, we also did a planning level feasibility assessment. So the city has a risk they use internally to identify and mitigate for risks to the project, making it from planning through to construction. And it has 5 basic categories that we utilized in our planning feasibility assessment. This was a desktop analysis that we did, and really just trying to identify and make some initial mitigation steps for any risks that might happen to a project. For example, if we're near a TxDOT corridor and we know that we're going to require some additional coordination, making that kind of red flag now to plan for additional time in our schedule if this is a project that is going to move forward. Then again, we're moving through that next stage of our program development, the development solutions. And so this is another opportunity. We want to take a moment to pause and reevaluate where we're spending resources. So we did a screening at this develop solutions stage to identify for each site what kind of project to continue moving forward with through project development. We did a preliminary risk assessment. So for the sites where a major improvement is going to be pursued further, we did a field visit so that we can better understand site constraints and any additional feasibility things to consider that we can tell kind of in more detail than what a desktop analysis can do. And then moving through project development, our more traditional alternatives analysis, schematic design, documenting that process, and then moving into design coordination. So a little bit more on that project development screening. So we took those hazards that we identified in our first stage and combining that with the benefits and constraints identified in our prioritized locations phase. Each site was put into 4 buckets. So a major replacement project, those are a lot of those projects that were in that green category that we feel good about moving forward to construction. Safety improvements, so for sites where we're pretty confident and we're not going to be able to move forward with the major improvement within the constraints of this program, we can still provide an increased safety factor using other elements. There's some projects that we recommended for a future bond program. So these are projects that cost maybe above the limitations of this hazardous roadway overtopping program, but it's a good project and could be considered as a standalone for a future bond. And then finally, we did evaluate roadway closures at each site. Roadway closure is a great way to completely eliminate the hazard of a roadway overtopping, but obviously is a big inconvenience to the public. And so that was evaluated at all the sites, but has limited applications. So for those projects where that major improvement was selected, we then move forward into an alternatives analysis phase, doing a detailed H&H analysis, evaluating what different levels of service look like in terms of reducing hazard at a site and what that cost associated is. So this is where we get into more of our traditional benefit cost analysis. And then documenting all of that effort through a schematic design. Freese and Nichols had the opportunity to work with the city through that preliminary analysis phase and into the project development phase. But in order to meet the aggressive schedule and getting all of these sites to actually construct these projects, the city has identified a group of design firms that are going to be picking up individual sites to really carry that project across the finish line. And so one of the really important tasks at this stage was to ensure that there was a solid, seamless knowledge transfer between the efforts to date and moving forward through to design. And so Freese and Nichols has had workshops with the design firm so that they can understand our scope of work, what we know, what we don't know yet, and really is geared towards reducing the uncertainty as these projects get scoped into design contracts. We have deliverables that we've developed to fully document the decisions made to date so that we aren't going backwards in any of our design efforts and can really increase the efficiency moving forward. So here's a little preview. That's where we are today. We're just in that transition, moving out of project development towards the design phase. And so here's a preview. We're looking at these major replacement projects. This is an example of a project the city took on in 2012, really increasing the capacity at the roadway crossing. Also, as a part of this hazardous roadway overtopping program, implementing safety improvements. So preparing the plans to really increase the understanding of risk at all of these sites of that life safety hazard, so that we know that they're hazardous. We don't have the funds to fix every site across the city today, but for those most hazardous sites, we can at least increase the understanding of the hazard at these locations. And we have a roadmap. So looking forward, like I said, we're moving out of that project development phase towards that design phase currently. And so, this has been a rock and roll schedule. So we really started the planning efforts in 2019, moving into project development in 2020, and already by 2021 are looking to have 3 major replacement sites designed, and looking forward in the next 5 years having a total of 11 major replacement sites and 30 safety improvement sites. And so a real big key to this whole program development effort is not only to just identify all of these sites, but to get something constructed. And so we have that roadmap of how we're going to get there, and hopefully through each stage, reevaluating where we're spending funds, we can meet this aggressive schedule. So just to provide some final thoughts on Fort Worth's hazardous roadway overtopping program, the Stormwater Department was really tasked with this huge challenge. There are hazardous roadway sites located all across the city in a variety of shapes and sizes. We have our typical low water crossings that we all kind of think of when we think about flooding over a roadway, but we also have things that appear to be a large crossing with a lot of capacity that are actually a hazardous location, and maybe the community doesn't fully understand the hazard at that site. And so this program was really focused on identifying the locations with the most hazard, where the city's financial resources can go the farthest in addressing that hazard and improving the safety of the community. At each stage, we really tried to focus on reevaluating, where to continue pushing forward. And so really focusing on an asset management style approach to mitigation. And so that's been our approach to addressing these hazardous roadway overtoppings for the city of Fort Worth. I want to thank you for listening to our presentation today. We're going to go into our live Q&A portion next, but if we don't have a chance to answer your questions, here's our contact information. Thanks.
Great. Thanks, guys, for that presentation. So this first question, Holly, is going to be for you, I think. What process did you use for GIS data collection? And were the sites identified by city staff or the public?
Yeah, so the city had completed an inventory of these hazardous roadway overtopping sites back in 2007. And so this effort was expanding upon that initial effort, which was really just kind of a field investigation with a paper form filling out based off of the field visit alone what the site conditions looked like. As a part of this planning effort, we did review, the city has in their GIS files their flooding reports. And so we went through and reviewed if there were any sites that should be added. They've been collecting that data in GIS since 2009. And so we were able to add, I'd say about 10 to 20 additional sites from just those reported flooding incidents.
Great. So Kiran, maybe you could talk about, with so many stormwater needs across the city, why is this HROM program such a high priority?
Yeah, the HRO program, it is a high priority because, as said, overtopping has been dangerous, even life-threatening at some of these locations, and there were fatalities associated with the hazardous road overtopping within the city, in the past, and and even in 2018-19, where we had incidents and fatalities reported and had a lot of media attention. So yes, this is an important, even though we have a lot of other needs. Not that I'm saying those are not important, but this is top, the topmost priority we have.
And did you have any opposition to this kind of a program because you were increasing fees?
So we did have stakeholder engagement before we went ahead and asked for the fee increase. The general consensus from the stakeholders was, yes, this has life safety consequences, and the consensus was, yeah, they did support, and and with the media attention we were able to get the 6.5% increase.
Yeah. So we have a couple of questions that have come in since I looked. So I'm going to ask another one, which is, well, actually, you just talked about stakeholder engagement. Maybe you could talk about the processes that you use to get that stakeholder engagement and consultation.
So, whenever we have some important updates, especially with this program and, with the incidents, so we include stakeholder consensus. So, the meeting was set up and there were several groups that were involved, including the development side and the community side. And, when we presented this and, the risk associated with this, I think, a lot of questions were answered. But the general understanding was, yes, this is a high priority, and the support was there to ask for a fee increase.
So has the city considered using FEMA hazard mitigation assistance funds to do any of these projects?
So yes, we did consider, and recently we were looking at this approach, but on the cost benefit side, I think it plays a major role on the cost benefit side, because traditionally with the flood mitigation projects, you have structures associated in the cost benefit. This is a roadway project where you're trying to elevate the road. The cost benefit plays a big role, and it depends on what percentage we get in the grant. Some of these might qualify, but again, when it comes to cost benefit, that's where I think we have to be careful.
Yeah, it's a lot harder to do for those kinds of roadway projects. So another question came in. Can you talk about how you incorporated equity into your decision-making process?
So all this prioritization was based on hazard. And, when we have approximately 300 sites where we are scoring based on hazard, there will be several sites that might have the same hazard score. And when we hit the same hazard score, now which project to be picked, the decision making comes on what other elements can be considered in picking the project that has the same hazard score. One of that is equity, where if the project is in the super majority minority area, we could add more, because it also has that element we can pick that project because all these projects have the same hazard score.
Okay, great. So maybe, are you going to be able to eliminate every hazard through this program?
Technically, we have like a 5-year plan right now. But again, this is all funding driven. And no, it is not practical to completely eliminate all the flood risk. But however, with this program, we will try to significantly reduce the hazards with reconstruction. Our plan is to address at least 40 sites with either construction or safety. It will be a mix of both with some road improvements as well as safety improvements. But the goal is in the next 5 years, we'll implement at least 40.
So somebody else just asked another question that came into my mind as you were talking too. So I'm glad somebody else asked it, which is, has the city considered any new regulations or design standards that would prevent new at-risk roads from being constructed in the future?
So right now, our design standard is, any new roadway, generally we typically design it for 100-year level of service. So yeah, the development side, any new construction going on, that's our standard.
Okay, cool. I don't see any other questions. Is there anything else you want to cover that maybe you weren't able to squeeze into the presentation?
I think touching on what Kiran was just talking about with the new development, what I found to be a trend looking through all of these sites is that frequently it was areas that were recently annexed that didn't get developed to City of Fort Worth standards, and were the ones that were missing either enough capacity or missing some key safety components like guardrails. So this program can kind of help as annexation continues. We may inherit some more, but ideally, the new roads being developed in Fort Worth shouldn't have the same issues.
That makes a lot of sense. Actually, we got another one. So does the city have a flood warning system for roadway sites that can't be mitigated through this program?
Yes, right now we have 50 hazardous road overtopping locations where we have flashes installed. And these are monitored, and we have a website that shows, the real-time monitoring of, where the level is and is the roadway overtopping. So we still plan to expand that, but as part of this program, the safety measures is a comprehensive look. It's not just flood warning, but it's also, when I say flood warning, it includes signage, also making the crossing safer, like lighting or putting additional guardrails to, so it's a comprehensive look, including flashes.
Great. Well, thank you guys so much. Great presentation and great Q&A. Thanks.
Thank you.
And thank you everyone for attending this session, and hope you enjoy the rest of the conference.